Good day to us all. So here we go. We're tying everything together, translations, stretches, reflections. It can all be summarized in this form right here. So inside of our parent function, all of this stuff affects the horizontal state of our function. The b, the coefficient of the x, that's for a horizontal stretch with the scale factor, not of b, but of 1 over b, reciprocal. The h is our horizontal translation. And remember, the horizontal translation is always opposite of the sign in the problem. So what that means is if it says x plus 2, we're really going to the left 2 units. Outside of our function, the a and the k. K is our vertical translation. And yes, it's exactly what it says. If it says plus 1, we go up 1. A is going to be our vertical stretch. And just like the translation, it's exactly what it says. If it says times 2, the scale factor is times 2. So notice in the parentheses inside the function, to read the scale factor in the translation, I have factored this horizontal stretch out. That, I think, is the most effective way of doing this. There are ways to do it without factoring the scale factor out, but I think it makes it more complicated. When you're applying these transformations, apply stretches first. Then translate. And this only works, again, if the thing inside the parentheses, if that is in a factored form. Remember that the translation can also be given in its vector form, h on top, k on the bottom. So let's dive in and look at an example. So here we have this graph for f of x. I want to sketch the corresponding graph under this mess of transformations. So let's identify what they all are first. So there's a vertical translation of up 3. To find the horizontal translation, remember, we want to factor what's inside the function. 2 times x plus 1/2. So my horizontal translation is going to be left 1/2. If we're giving this in vector notation, it would be negative 1/2, 3. But I'm waiting on that stuff. I don't want to do anything with the translation yet. I first want to do my stretches. And in this problem, there's both horizontal and vertical. There's a horizontal stretch with a scale factor of 1/2. There is a vertical stretch with a scale factor of 2. And what's the deal with the minus? Well, that's a vertical reflection. So there is a lot of stuff going on here, and we're going to do it one bit at a time. I'm going to start with my horizontal stretch. So all of the points, all of the coordinates get closer to the y-axis by half. So this point that's at negative 5, 2, it is now going to be at negative 2.5, 2. This point that's at 2, negative 1 will be here at 1, negative 1. This point that's at 3, 4 will be at 1.5, 4. And this open endpoint that is at 5, 4 will be at 2.5, 4, and it will still be an open dot. So if that was the only transformation I had, we'd connect the dots and be done. This y-intercept is a stationary point. It's a fixed point under this transformation. So there's our horizontal stretch. But we also have vertical stretch and reflection. So let's move these points yet again. I'm going to reflect and stretch at the same time. So I'm going to make them twice as far away. So this point is going to double in height. It's at a height of 2. I want to go twice as far away. So it's going to jump up to 4, but then reflect, so it's 4 units under. 1, 2, 3, 4. Same with this point. It's going to go twice as tall, but reflect. This point, twice as tall, but reflect. These points, twice as tall, so it's going to be at 8, and then reflect. So it's going to be here, and one more point to reflect, and stretch to right there. And if all I was doing was stretching, if there was no translation whatsoever, I'd be connecting my dots, and I'd be done. This would be what the transformation looks like under these 3 transformations. But there's more. We need to now move these points to the left 1/2 and up 3. So left 1/2, up 3. Those of you that like using colors, this is a very appropriate section for it. Otherwise, erasers are real good to get rid of all these extra points that we don't really need anymore. But everything's just bumping over 1/2 and going up 3. And now I can connect my dots, and we have our finished product. A finished graph that is these black lines and points. And I hope you caught that I made a mistake over here on the end. That should really be an open dot. And there we are. There's our fully transformed graph from y equals f of x. Let's look at another problem. Here we have 2 graphs. We have y equals x squared, and we have this transformed one, but we're not really told what the transformations are. We have to figure them out. Well, I see the image graph g of x is reflected. So we know there's a vertical reflection. That is a reflection in the x-axis. There's also a translation of left 3, up 2. And we really don't know anything else about the shape. We don't know if there was a stretch. It looks like there wasn't. They don't give us enough information to say that there is, so we're going to just say that there is no stretch. Now we plug stuff in to this. We transform this. So a vertical reflection, that's where we make the function negative. We're moving to the left 3. So x plus 3. That's how we would show that in our function. And up 2. There's our g of x. But notice that we want this written in standard form, not this would be vertex form, wouldn't it? So how do we get there? Well, we expand. Please don't kill any puppies. Don't distribute this exponent. Save the puppies, ladies and gentlemen. Remember to FOIL. Now we distribute the negative. collect like terms, and we are done. And if we wanted to check to make sure that we were at least in the right ballpark, we could take our graphing calculator out. We could graph y equals x squared, and we could graph this pig function g of x, and make sure that our picture does indeed look like that. Remember the rule of thumb though, going back to this, stretch first, then translate. It's just like athletics, ladies and gentlemen. If you don't stretch first, you will hurt yourself. Have a wonderful day.